Welcome to the seminar Búsqueda de Nueva Física en Aceleradores y el Cosmos. Today we have a presentation from Sven Stawinski from the University of Bonn. A brief background about him. He did his undergraduate studies at the University of Kaiserslautern in Germany. He has a master's degree from the University of Cambridge in UK, and he is currently pursuing his PhD at the University of Bonn in Germany. So welcome, Sven, and when you're ready, please go ahead.
Okay, thank you very much. So thank you very much for the invitation. I had the pleasure to be in Puebla in person earlier this year, and so it's great to be back over Zoom. So my goal was to give a hopefully pedagogical introduction to sort of the ideas and methods that go into the modern techniques for Feynman integrals. And I will be trying to build up to some recent work I've been doing together with Claude Dour and Franziska Borchert. So just as a brief motivation, well, as you all of course know, QFT or quantum field theory is the natural synthesis of quantum mechanics and special relativity, and as such is the unique and correct language for fundamental physics, at least at energy scales accessible to us. However, if we try to get a prediction out of quantum field theory, if we try to compute something concrete, then probably everybody has made the observation before that this is typically very difficult. However, what has been realized over the last couple of decades is that the answers that QFT gives us are often not as difficult as the computations are. So there's somehow some hidden simplicity in the results that is not clear where it comes from the outset, and seems to be hinting at us maybe doing QFT in the wrong way in some sense. And so from this observation, there has been sort of an emerging paradigm over the last couple of decades, which you could call the scattering amplitudes program, with scattering amplitudes being one of the main calculable quantities that people have focused on and observed these hidden simplicities. And the idea of this program is very basic. Really, people just try to do as many computations, push it as far as they can. And then in the answers to these computations, they look for structures, for some simplicity, try to understand why things are maybe simpler than expected, what structures underlie the results. And this typically then gives rise to new calculational methods, new insights, which lets us push the boundary of what is computable even further. And this cycle has been going on for some time. And so in these computations, there are typically sort of two main difficulties, two main areas of complexity, I would say. And so first of all, you have what I would call combinatorial complexity, which just comes from us having to draw all of the Feynman diagrams and putting them into formulas and adding everything up. And as you have probably realized before, this is a mess. So even if I just do 5 gluon amplitudes at tree level, I have to draw thousands of diagrams. But the answer could be very, very simple. And so people have been developing ideas and methods to circumvent this tedious drawing down Feynman diagrams to immediately get to the answer of the sum of the Feynman diagrams in the sense of finding tree amplitudes or loop integrands. However, if we will go beyond tree level, these loop integrands are of course not the end of the story. We still have some integrals to do. And so this is the next area of complexity. Namely, these integrals are typically very difficult, and we need methods to tackle them, to solve them in some sense. And so this is going to be what I will be focusing on. And so if you want to understand the integrals that we need to solve, well, we have to ask what kind of integrals quantum field theory gives us, and this has a very precise answer, namely the family of so-called Feynman integrals. And one can define them very generally in the following way. We have some integrations over space-time. The number of integrations corresponds to the number of loops in a respective Feynman diagram. And then we have a universal denominator, which is just a product of propagator factors and just reflects the topology of the diagram and is universal, while we have some numerator structure, which then encodes the precise interactions and the particles that are involved. And so in the spirit of this amplitudes program mentality that I introduced on the last slide, the goal should be clear. We should try to compute as many and as complicated Feynman integrals as possible and try to understand the results. So from what I've said so far, this quest or this idea is not very well defined, because Feynman integrals are, of course, as many things in quantum field theory, typically divergent objects. And so we need to assign some meaning to them. We need to regularize. And there are very many options how we could do this. We could introduce some Pauli-Villers ghosts. We could put some analytic regulators on all of the propagators. We could simply cut off the divergences, just put a UV cutoff or some IR cutoff in this form of some auxiliary masses. All of this would work, but really the most practical way of doing this, and the way pretty much every modern computation is done, is dimensional regularization. And the idea is very simple. We just analytically continue in the space-time dimension to some generic complex value. And then we expand the resulting analytic function in a Laurent expansion around the integer space-time dimension we're actually interested in. And so it is really these Laurent coefficients in this expansion that we are interested in. And so when I say compute a Feynman integral, I really mean low-lying Laurent coefficients in this series. So what kind of functions are these? Well, naively, these could, of course, depend on all of the external momenta and all of the masses of the internal exchange states. However, we typically are interested in, at least in fundamental physics, we are interested in Lorentz invariant theories. And so really, these functions can only depend on Lorentz invariant combinations of these external momenta. So we could have some dot products, which are typically referred to as Mandelstam invariants. We could have some squares, which are just the external masses, and of course the masses of the internal states. However, this is not all. Feynman integral, just by power counting, has some fixed mass dimension, some fixed energy dimension if you want. And so we can just write down this energy dependence using any scale just by dimensional analysis. And then what is left over does not carry units anymore. So it has to only depend on dimensionless ratios of some of our variables. And so this reduces the amount of variables we need by one. So just as a brief example, if we look at a 4-point integral, which only involves massless particles, then naively we have all 4 momenta to worry about, but Lorentz invariance immediately drops this down to 2 variables only, which are the Mandelstam invariants, typically denoted by S and T. And then we can use this scaling invariance to just, or dimensional analysis to just write down the dimension dependence using S, for example. And then the rest will only be a function of a single variable, which is just the ratio of these 2 Mandelstam invariants. So such an integral is really a function of a single variable. And so when I say Feynman integral in the following, I will always mean this function of kinematic or dimensionless ratios of kinematic invariants. Okay, so we want to compute these. So the question is, of course, how? I mean, this is, of course, the big question. There is no perfect answer to this. But many different methods have been developed over the last decades. And of course, we can just use numerical methods. We can just put things on a computer using some sophisticated algorithms and get numbers out. And there are many ways of doing this. Many methods have been developed here, but since we want to understand the structure of the results, this won't get us very much, because we can't really see much structures from the numbers we get. So we really need some analytic techniques. And of course, we could try to do it as we learned in the first QFT course. We could use some parametric representation and just try to integrate it. And this indeed works in some simple examples, but it doesn't get us very far. The method that has been the most powerful for quite some time is the so-called Mellin-Barnes method. The idea is just to change or switch, trade the loop momentum integrations for some contour integrations that you can then solve by residues in terms of some series. So it gives you a power series representation of the integral. However, this is for many purposes not very nice. And indeed, this method has by now been completely overtaken by the differential equations method, which is pretty much exclusively used nowadays. So it's really the method with which all of the modern multi-loop computations are done. And so this is the method I want to focus on in my talk and review in the following. So to get to this method, I need to introduce a very important idea, namely the idea of an integral family. So if we start with some Feynman integral, as I said, it's sort of invariant, or its characteristic features are the denominators. So let me just take the denominators of some Feynman integral, the propagators, and allow arbitrary propagator powers. So I allow them to be raised to arbitrary integers. So if I put all integers to 1, I just have an ordinary Feynman integral with unit numerator. But I could also put the propagator powers to some negative integer that would correspond to something in some non-trivial numerator. Or I could consider propagator powers larger than 1, so positive integers. This is, of course, a priori an unphysical integral, but it is, at the moment, part of my definition of an integral family. So it might seem a bit weird. Why does this make sense to do? I mean, I've traded a single integral for an infinite family of them. Well, really, the important reason is that there is a very fundamental result, namely that this infinite set of Feynman integrals actually has a very nice mathematical structure, and that it forms a vector space of finite dimension. So finite dimension means it has a finite basis. So it can express every Feynman integral in this infinite family as a finite linear combination of some basis elements, which are typically referred to as master integrals. And this decomposition to the basis is typically, or is from a conceptual point of view, actually trivial. I can typically do it just by integrating by parts an appropriate number of times in certain ways. However, this is conceptually very straightforward, but in practice that can be a mess and is actually a bottleneck for many cutting-edge computations. But I will not really focus on this issue in the following. For all examples you will see in my talk, this is a trivial problem. So there is a very simple corollary, which is, however, very important, namely that, well, if our vector space has a finite dimension, then we can use this to derive some first-order differential equation. And the reason for this is very simple. If I differentiate some Feynman integral with respect to some of its variables, then, okay, I might raise some propagator power, I maybe introduce a numerator factor, but I will not create a new propagator out of nowhere. So this family of Feynman integrals that I defined should be closed under differentiation. And so in particular, if I take some list of master integrals, so a basis for my vector space, and put it into a vector, and I take the differential of it, then it's still in the same family. So I should be able to re-express it in terms of the basis elements. And so this naturally gives me such a matrix differential equation, first order differential equation for the master integrals. So here on the left-hand side, I'm taking a total differential. So I'm packaging all of the different first order partial derivatives that I could take into a one form. And so the right-hand side, this matrix is really a matrix valued one form. And very importantly, because I can do this decomposition into a master integral basis just by integration by parts, this will have rational dependence on the kinematic variables and on the dimensional regulator. So, of course, we have now traded the task of integrating certain Feynman integral for solving a first-order differential equation. So what does this buy us? Well, the idea, or the main point, is a key idea by Johannes Henn of about 10 years ago, that if we find a suitable change of basis of this vector space, then we can actually trivialize solving this differential equation and thereby solve the Feynman integral. So let's see how this works. Say I have some basis for my vector space I, so a set of master integrals, and I now rotate it with some matrix R into a new basis. And then, well, also this new basis will satisfy some first order differential equation, but now the new differential equation matrix can be obtained from the old one by essentially a non-abelian gauge transformation. And so the key insight of Henn was now that, well, if we choose this rotation in such a way that the new differential equation matrix has trivial epsilon dependence in the sense that epsilon is factorized out, so it's only appears as a linear prefactor, then the solution to this equation in dimensional regularization, so in an epsilon expansion, is trivial because we can just write down the solution in a formal way by writing down the path-ordered exponential of the differential equation matrix. And now you see that, well, the epsilon expansion is nothing else but the Taylor expansion of this exponential. And so if I want to read off some Laurent coefficient in this Taylor expansion, well, I just have to, in this epsilon expansion, I just have to read off the corresponding coefficient in the Taylor expansion of this exponential. And so Johannes Henn conjectured, well, first of all, observed this in a couple of examples and conjectured that, first of all, this is always possible. So I can always find a rotation into such a basis where this epsilon is factorized out. But he conjectured even more than that, namely that there should be a way of doing this where not only the epsilon is factorized out, but also this differential equation matrix that you find in the end has some additional nice properties, such as, for example, only logarithmic singularities. And this he called canonical basis. And so the conjecture is that such a canonical basis always exists. However, I should say that this is not very well defined. So there is no completely agreed upon definition of canonical basis. So it's not fully clear what extra conditions we should have on this matrix. So this is still an ongoing topic of research, but that is not going to be so important for the rest of the talk. So let's see how this would work in practice if we have found such a canonical form. So as I already said, really all we have to do is expand the exponential, and this works in precisely the same way as the Dyson series in ordinary quantum mechanics. So let's take a very simple example where our canonical differential equation matrix only contains two different one forms. So we can just write it as a sum of two matrices, each just being a constant matrix, so matrix of numbers times the respective one form. And also just assume for the moment that we have a one variable problem so that the formulas are less tedious. And then, well, all I have to do is I just have to expand this exponential. So at first non-trivial order, all I find are just these constant matrices times the integral of the one forms that appear in my differential equation matrix. And at the second order, well, I find a double integral, but very importantly, due to this path ordering, these integrals will be iterated. So I naturally find this nested iterated structure in the integrals. And well, okay, this was a very simple example, but hopefully it is clear that this will always happen. So from this, we can immediately find that Feynman integrals in dimensional regularization are very naturally evaluated in terms of iterated integrals. And well, we saw these iterated integrals in a simple one variable example, but we can define these objects for any number of variables, as was done a long time ago by Chen, and he studied them from a mathematical point of view. And so the way to define them is, well, we have to choose a base point. This will be the point where we give the boundary condition to the differential equation. So it should be some point where we have good control over the Feynman integral. Maybe we can integrate directly, or it is some singularity and we can control the asymptotic behavior around the singularity or something like this. And then we have to choose a path from this base point to the point we're interested in. And very importantly, one can show that this Feynman integral will not depend on the details of this path. A mathematician would call it homotopy invariant, so we can deform the path a bit and the value of the integral won't change. However, of course, there will be some singularities in the integrands, and if our path crosses one of these singularities, we will pick up some residue. And indeed, the value of the integral will then change. But this just reflects the fact that the iterated integrals we get, and therefore also the scattering amplitudes, will be multi-valued function of the kinematics. But this, of course, has to happen due to the optical theorem, for example. And so choosing this path really is nothing else but choosing the branch of the function that we get out. And so, okay, if we have this path, we take our set of one forms that we want to iteratively integrate and just pull them back to this path, and then just integrate this function up iteratively, as you see here. And just as some terminology, these one forms that appear in the canonical differential equation matrix are typically referred to as the letters of the integral, or letters of the scattering amplitude, if you want. So these iterated integrals are the natural building blocks of Feynman integrals. And so let's study a very important example of iterated integrals that appear. Namely, I already told you that the letters, so the one forms in the canonical differential equation matrix, are expected or conjectured to have at most logarithmic singularities. And well, a very obvious way of satisfying this are D-log forms. Well, they by definition have logarithmic singularities, and indeed they often appear in differential equation matrices. And so if we just plug these types of one forms into our definition of iterated integrals, we find the following form of integrals. And indeed, these are functions that are well studied in mathematics. They are referred to as multiple polylogarithms. They have been known for hundreds of years, but in the modern literature, they have been studied by Goncharov, and they are very well under control. And happily, this sort of trivial way of satisfying the restrictions of a canonical form is actually sufficient for a lot of amplitudes, in particular for all one-loop amplitudes. So all one-loop amplitudes can be expressed in terms of this class of multiple polylogarithms. And this understanding of the differential equation method and this space of functions has actually led to what people have called the NLO revolution, so next to leading order revolution, leading to the full solution of integrating one-loop Feynman integrals, and then in the next step to a whole lot of predictions for the LHC, for example, at next to leading order. And not only the differential equation method is the reason for this revolution, but also the good control over these functions. And this really comes from some very powerful algebraic structures that underlie these functions, which I unfortunately don't have time to talk about today. But I can just tell you that these algebraic structures give us a very good analytic control in the sense that we can completely control the functional relations between these objects and also their singularity structure. So where their branch cuts are, where poles are on different sheets and stuff like this. So we have seen so far that solving a Feynman integral is pretty much the same thing as finding a canonical transformation or finding a canonical basis for its differential equations. So the obvious question is, of course, how do we find this canonical basis? And indeed, this is an open question in general. People are trying very hard to find an answer to this. But one very important tool has emerged, has been proposed a long time ago, but its importance is realized over and over again, which is the topic, is the notion of leading singularity. And so the basic idea of a leading singularity of a Feynman integral is to just start with the Feynman integral we're interested in, and it's typically given by some integrand integrated over something like R4. And what we do now is we just deform the contour in such a way that the integral simplifies. So as a very simple example, let us look at this Feynman integral with 4 propagators, would correspond to a box diagram. And you can see where it has 4 propagators, there should be some 4 singularities in this integration domain. And so what we do now, we don't integrate over R4, but rather we integrate over some 4-dimensional torus, which just encircles all of these 4 poles. And really this just computes a residue, or 4 residues, and it will fully localize the integral. And so while the original integral might be difficult, the leading singularity, the integral with deformed contour, fully localizes in just an algebraic function of the kinematics. Okay, so I mean, this is something we can define, but the question is, what does it have to do with canonical basis? Well, the key observation here is that we conjecture that in the canonical basis, the letters, so the one forms that will appear in the iterated integrals, have at most logarithmic singularities. And if they have logarithmic singularities, then the residues will be 1 or 0. I mean, I can kill them, of course, if I take a residue somewhere where they don't have a singularity, but else I will always get plus or minus 1, depending on the orientation of the contour. And so if I take such a leading singularity of an iterated integral of such canonical letters, so letters with logarithmic singularities, I'll always get 0 plus or minus 1. And these functions, which have so-called unit leading singularities, are typically referred to as pure functions in the physics literature. And just as a very simple example, you can look at this prime example of iterated integral we found, namely this Goncharov polylogarithm, which just arose from D-log forms in the canonical differential equation matrix, just as a trivial example of forms with logarithmic singularities. And indeed, I mean, we have some contour which looks like a simplex or so, which just corresponds to this iterative integration. But I mean, we're supposed to deform this, so let's just look at the integrand. And of course, we can just encircle all of these n poles, and we just get a number out of it. And we can normalize it to be 1 or plus or minus 1. And so we expect the solutions to a canonical differential equation to have unit leading singularities. So if we start with any integral, we should somehow get the canonical integrals by normalizing to unit leading singularities. So the schematic idea is if I take some integral, I compute its leading singularities, I sort of divide out by it to get something with unit leading singularities, and then this should be the canonical integral. And so the rotation into the canonical basis is morally just dividing out the leading singularities. I mean, this is very schematic. Of course, an integral can have multiple leading singularities, so there might be multiple ways of taking a bunch of residues. And I have to normalize all of these leading singularities to one. For this, I might have to introduce some smart numerator factors. Maybe I have to take some linear combination of integrals. But morally, we really just divide out the leading singularity. And this has been understood in a more or less algorithmic way and has been implemented in public codes. And so one can ask, well, this seems like this problem is solved, right? I mean, we can just put our favorite problem into these codes and get out the answer. But of course, this is not quite true, because I've left out a very obvious obstruction, namely, it might not be possible to fully localize the integral. So say I have some integral and I cannot I take as many residues as I can, but I don't fully localize the integral, then it's not clear what I have to do. So the famous counterexample to this algebraic leading singularity we saw before is this sunrise integral. This has already been noted in the 60s. Namely, if I take this very simple sunrise integral and take as many residues of its integrand as I can, I will end up with something like this. So this is still a single integral. The integrand is a square root of a fourth order polynomial. So this clearly doesn't have a residue anymore, but it's also not localized. So what am I supposed to do with this? So first of all, it's not clear what the leading singularity now means. Also, I mean, it should somehow mean that we should deform the contour in a nice way. So we should put some good choice of gamma, but it's a priori not clear what a good choice of gamma is. So from the outset, it's not clear how to proceed. So the idea is to study this in a toy example, in a setup that is as clean as possible, where we can maybe see the solution to this problem as easy as possible. And so just as as a remark, these integrals that we get by just taking as many residues as we can until we don't have any residues left are typically referred to as maximal cuts of Feynman integrals. And so typically, at least in the simplest case, these maximal cuts would be single integrals over such a square root. And so a toy example for these maximal cuts are just simple hypergeometric functions. And so the simplest hypergeometric function we can think of is the Gauss hypergeometric function, 2f1. And so we will study an integral like this, which is just the integral representation of the Gauss hypergeometric function, where we have three linear factors with zeros at 0, 1, and a parameter psi inverse. And I will give these three linear factors some exponents, which correspond to the parameters of the hypergeometric function. I will first give them some integer exponents. These correspond to these labels of the Feynman integral family, if you want. So they could, for example, correspond to some numerator polynomials that survive in the maximal cut. I then put a -1/2 in all of the exponents. This is just supposed to resemble the square root that we found in the maximal cut of the sunrise integral, and that will actually happen quite generically for these maximal cuts of Feynman integrals. And I will put some rational prefactor of some generic parameter, which I call epsilon. So this should just resemble dimensional regularization, which we typically use. Okay, so this is a toy model for this maximal cut, and it turns out that it will have all of the ingredients that will allow us to find the solution to this problem for Feynman integrals. So let us just proceed in the same way as we would do for Feynman integrals. So let us try to set up a differential equation. And so what we have to do, well, we have to choose a basis of master integrals. So a basis for this vector space of all of these Tn's. So this is a family where the n's can take any integer values, and it turns out that this family has a two-dimensional basis given by these two choices of n's. And I can write the integrands in the following form, where I just write this square root as y, and I write this dimensional regularization part as psi, and then the rest is just 1 in the first case and x in the second one. So these are the two master integrals. So just to derive the differential equation, I just differentiate them and re-express the result in terms of the master integrals, and I find the following very simple first-order differential equation. And so indeed, as promised, this has a rational psi dependence Also very simple rational dependence on the dimensional regularization parameter epsilon. However, it's clearly not factorized, epsilon factorized. So what we want to understand is how to bring this into a canonical form. And in the process of doing this, we should probably understand what the leading singularity means in this case. And in particular, what the good choice of gamma would be in the that we saw, for example, in the definition of the hypergeometric function or in the maximal cut of the sunrise integral that we saw before. And the key insight in solving these problems comes from geometry. Namely this y that I defined earlier, that defines the square root that appears in the maximal cut or in the hypergeometric function, actually defines an algebraic variety, which is called an elliptic curve. So, I mean, y is a square root, so y squared is a polynomial. And so this is an algebraic equation, and the solution set to this algebraic equation, so the set of x and y, which are both complex numbers that satisfy this polynomial constraint, is precisely what mathematicians call an elliptic curve. And here you can just see an image, for example, of this point set projected to the reals, of course, so I can put it on a plane. And so how should we think about this elliptic curve? Well, let's think about it in the complex x plane. So for almost all values of x, there will be two solutions to this equation, corresponding to the plus and minus sign in the square root. And so I should think of two copies of the complex plane. However, there are four special points where there is only a single solution, namely 0, 1, psi inverse, and infinity. And so these are branch points for this double covering of the complex plane. And so I should draw branch cuts between them so that I cannot encircle the branch points. And then I have to glue the two branches, the two sheets, the two copies of the complex plane along these branch cuts. And if I now think about each of the complex planes as a sphere, so I just add infinity to both of them, then I have two spheres, each with two cuts. And if I glue them, I hope it's clear that I get a torus. And so pictorially, you could think of this elliptic curve as a torus. And now with this torus picture in mind, you directly see that there are two very natural cycles that we can choose on this space. Namely, the one that goes sort of around the torus and one that goes along the handle of the torus. So we have two non-trivial cycles, which are typically referred to as A and B. And so these are very natural choices for the leading for the integration contour in the leading singularity, which we called gamma before. We can also see this in this complex X plane, that there are two non-trivial cycles, namely where we can clearly take a cycle that goes around one of the branch cuts. This is referred to as an A cycle. Or we can take a cycle that starts on a branch cut, goes to the other one, changes the sheet, and comes back to close the cycle. This is referred to as a B-type cycle. So I have these two kinds of cycles, A and B. So we have two natural choices, but which is the right one? Which is the leading singularity? This is still not clear. And a good answer to this question, again, comes from mathematics. So these two cycles that we found span what mathematicians call homology. So this is just the space, it's a vector space of closed contours, so contours that do not have a boundary, modulo contours that are a boundary themselves. And we already saw two examples, the A and the B cycle, and indeed this will be a basis for this homology of the elliptic curve. However, also the integrands we saw before span an interesting space, namely what people will call cohomology. This is just the space of the closed forms, so forms that are annihilated by the total differential, modulo exact forms, so forms that are a total differential of something else. And also these integrands are that we found are classified by mathematicians, namely into a first kind differential form, which just means it's holomorphic. It doesn't have any poles, doesn't have any singularities. And a second kind differential form, which just means it has poles, but no residues. And our two integrands, our two master integrals that we found for this hypergeometric function precisely match these two criteria. They're a first kind, they're a second kind differential, and they will span the cohomology of the elliptic curve. And so we found actually two very natural contours, A and B, and we found two very natural cohomology elements just as the master integrals of our problem. And now there's a very natural pairing between these two spaces. which makes these spaces in some sense dual to each other, which is referred to as period map. Namely, I can just take an integrand from the cohomology and some contour from the homology and just integrate the integrand on the contour to get a complex number out. And precisely this pairing I can now do for all combinations out of these basis elements. I will get a 2x2 matrix, which is referred to as period matrix. So I just take the two natural choices of contour in the two columns of the matrix, so the two homology basis elements. I take the two natural integrands I found, namely the master integrals, the elements spanning the cohomology in the two rows, and I form this 2x2 matrix. I can also give these things names. If I integrate a first kind differential, I would call it a period, omega 1 or omega 2, depending on which cycle we integrated on. And if I take a second kind differential and I integrate it, I will call the result a quasi-period, eta 1 or eta 2, depending on the A or B cycle. And so this seems like a very natural choice for the leading singularity, right? I mean, we took our residues, so we landed on the Maxwell cut, which is here resembled by this hypergeometric function. And we found from studying the differential equation that we have two natural basis integrands we can choose from and two natural contours we could choose from it. And so this is sort of seems like a natural generalization of leading singularity. And indeed, people have thought about this and tried this. And so, well, the first thing we should do to test this is to see, well, if we divide out by this leading singularity, which just means by multiplying by the inverse matrix. So we take our basis, our master integral basis that we found, divide out, so multiply by the inverse of the period matrix and see what happens. And indeed, the differential equation will be epsilon factorized after it. So this is already very nice. But unfortunately, this differential equation matrix that comes out does not have very nice properties. And so we would actually not like to call this canonical. So this seems like it almost worked, but it didn't quite work. And so this is a bit puzzling at the moment. I mean, this seemed like a very natural proposal. So what is the correct way of doing it? Well, people have found a way of doing this, which seems very ad hoc from the start, but has been just observed by direct computation. Namely, if we take this period matrix, remember this was just the two integrands integrate of the two contours, then we can split this matrix sort of into a product of two matrices in the following way. Here we use a quadratic relation between the periods and quasi-periods, which is referred to as Legendre relation, which is written down here. And in doing this, I can split the matrix into, first of all, a matrix which only depends on the period and quasi-period, which are integrated on the A cycle, so omega 1 and eta 1. And this matrix doesn't have any special requirements. It's just diagonalizable, which is also sometimes called semi-simple. And then we have a second period matrix, which only contains a particular combination of the two periods, namely the ratio. This is, first of all, a very important quantity on the elliptic curve. It is referred to as a modular parameter, and in some sense is a very natural variable for the elliptic curve since it parameterizes the geometry of the elliptic curve. And also this matrix has a very important property, namely it is unipotent, which just means if I take its differential equation, then the differential equation matrix appearing here just has an entry in the upper right corner. So if I square it, it will be 0. And so it is a unipotent matrix, or its differential equation matrix is a nilpotent matrix, which by definition makes this matrix a unipotent matrix. So I did very ad hoc splitting of this period matrix into what I call a semi-simple part and a unipotent part. And what these authors in this paper up here now realize is that if I divide out only the semi-simple part of the period matrix, then the resulting differential equation matrix will almost be in canonical form. And so I just have to do some extra rotations, some very trivial rescaling. So I don't have to do much. This was really the crucial step. And I land on an epsilon factorized differential equation matrix, which is extremely simple and we would like to call canonical. So as I said, the definition of canonical is not fully agreed upon, but this certainly is something we would like to call canonical. First of all, because it's very simple. Only the period, for example, appears, the quasi-period completely dropped out. only logarithmic singularities are there. And there is another surprise awaiting us, namely if we change variables from this parameter xi, which appeared in the definition of my hypergeometric function, to this modular parameter tau, which is very natural from the geometric point of view, then I find that I can split this differential equation matrix into 3 parts, each just being a constant matrix times either 1 or a function, which turns out to be a modular form. And so a modular form is just a holomorphic function which has a particularly nice transformation behavior under modular transformations. And so this is, first of all, mathematically extremely beautiful. So these modular forms have been studied a lot in mathematics. They have been playing a key role in the proof of Fermat's last theorem, for example. But this is also extremely nice from a practical point of view because we can evaluate these modular forms extremely fast. And so we can evaluate the iterated integrals about these modular forms, so the results to the canonical differential equations, very quickly. And so this is a very nice epsilon factorized differential equation and is something we would like to call canonical. And the key step was taking not the full period matrix, but only its semi-simple part. So, I mean, apart from this trick, it should be clear that really the key point in understanding how to find a canonical basis and generalize this notion of leading singularity in this case of the sunrise integral, or in its toy example, which is the Gauss hypergeometric function, was that we realized this connection to the elliptic curve, so the connection to geometry. And indeed, this has been sort of an emergent theme over the last 10 years or so, that it is very fruitful and seems like the right way of thinking about it, that we can associate to each Feynman integral some complex geometry and then use the properties, information from this geometry to understand things of the Feynman integral, like, for example, its differential equation. And it turns out that most Feynman integrals that have been studied to that point are sort of connected to a trivial geometry, namely just the Riemann spheres, so just the complex plane with a compactified by adding a point at infinity. And so this precisely corresponded to the integrals that we saw before, where just taking a bunch of residues fully localized the integral, so we had just algebraic leading singularities. It also corresponds to the integrals where the differential equation matrix only contains D-log forms, so trivially satisfies only logarithmic singularities. And so we already saw that these types of functions connected to the Riemann sphere are completely sufficient in one loop. However, starting at 2 loops, there are other things appearing. For example, we saw the sunrise integral, which was connected to an elliptic curve, which is sort of the simplest non-trivial geometry that appears in Feynman integral computations. But this is not the end of the story. This observation has really opened Pandora's box, and a lot of highly non-trivial geometries have emerged. And there are sort of 2 directions starting from the elliptic curve, how one can generalize, or how generalizations appear that play a role for Feynman integrals. And the first thing one can do is one can study higher dimensional varieties. These will be of so-called Calabi-Yau type and have been studied a lot in the string literature for completely different reasons, but now we can import the methods developed there to study Feynman integrals. There are also other geometries appearing which still have complex dimension 1, just like the elliptic curve, but have a higher genus, so have more holes if you want. And these are referred to as Riemann surfaces or higher genus Riemann surfaces. And these are what I will focus on in the following, in this talk. So, of course, we only saw, sort of observed that splitting the period matrix into semi-simple and uniportant parts seems to be a good idea, at least in this very simple example of the hypergeometric function. However, I should say that this method has by now been tested in a lot of cases and actually been turned into a sort of algorithm, although it's more of a recipe at the moment, I would say. And so it's been tested in a lot of highly non-trivial examples involving, first of all, a single elliptic curve, as we saw before, but also in examples where multiple elliptic curves appear. Also, K3 surfaces, which are more non-trivial geometries, have been studied, and also higher dimensional Calabi-Yau varieties have been shown to be treatable with this sort of splitting of the period matrix. And so what I would like to investigate in the rest of my talk, and which is what I'm currently working on together with Claude Doer and Franziska Porkert, is if this also works for higher genus Riemann surfaces. And well, the full space of Riemann surfaces is certainly too complicated at the moment, so we will focus on a very important but simpler special case, which are so-called hyperelliptic curves. And so let me define what that is. Well, this is actually very simple to define. It takes almost the same form as our definition of elliptic curve, where we had algebraic or polynomial equation y squared equals to a degree 3 polynomial. Now we just have a polynomial of degree 2g plus 1, where g will correspond to the genus of the hyperelliptic curve, so the number of holes in the surface. And the simplest Feynman diagram or Feynman integral that will give rise to such a geometry will already be at 2 loops. So the first loop order beyond the fully solved 1 loop order. However, it will not appear in the planar sector. I'm not aware of a planar 2-loop Feynman diagram which gives rise to something more complicated than an elliptic curve. But in the non-planar sector, this actually happens. This has been actually known for quite some time and also more recently been picked up again and shown that this Feynman diagram or this Feynman integral corresponds in some sense to a hyperelliptic curve of genus 2. And so we would like to study if this method of splitting the period matrix can also give us canonical differential equations, so can solve Feynman integrals, which will involve this hyperelliptic curve. And again, as before, we will try to study this in sort of the cleanest possible context. And while for the elliptic case, this was the Gauss hypergeometric function, here it will be a Lauricella function. And its integral representation looks very similar to what we saw before. We just have a bunch of linear factors, but now we have 5 zeros and not 3, and we have 3 variables and not 1. However, the exponents are still really the same. I have a minus 1/2 resembling the square root in the maximal cut. I have some integers which label my Feynman integral family, and I have some rational multiples of something that I want to interpret as dimensional regularization parameter. And so in the same way as before, or as I just defined, this square root that I put in here by hand and which will appear in the Feynman integral if I take its maximal cut, defines hyperelliptic curve of genus 2 indeed. So we have some degree 5 polynomial on the right-hand side, and by the correspondence I showed you on the last slide, this will be genus 2. And so now we can just proceed in the usual way. We find some master integrals for this space. It will turn out to be 4-dimensional. The integrands look very similar to before. I have this Dirac part always. I always have the square root. And then the integrands are pretty much just 1x, x squared, and x cubed. However, for technical reasons, I have to correct the x cubed one a bit. I have to put in a 3, and I have to put in some lower order terms, but this is not so important. This is just a technical point. So I have this list of 4 master integrals, and so I can compute their differential equations just by differentiating. And I will find something like this. Well, of course, this is very schematic. These are some rational functions, so nothing complicated, but it's just too big to put on a slide. So these are some rational 4x4 matrices. And so the goal is clear. We should find its canonical form. And the way we are trying to do this is to sort of generalize the algorithm or recipe proposed in the elliptic case, and that we saw in this very simple example earlier, to this hyperelliptic setting. And so the procedure is clear. We have to compute the period matrix and then try to split it. So to compute the period matrix, we again have to understand the homology and cohomology. And as before, the cohomology is simply spanned by our integrands that we already found from our master integral analysis. And as before, we can split our integrands into 2 types, into first kind, so holomorphic forms, and second kind, meromorphic forms, but without a residue. Now we however, have 2 of first and 2 of the second kind. And also the contours are very similar to before. We now have 6 branch points, so 3 branch cuts, and I can draw 4 non-trivial cycles on this. I will have 2 A-type cycles, which just each encircle one of the branch cuts. And I have two B-type cycles starting on a branch cut, going to a different one, and coming back on the other sheet. So I have four-dimensional cohomology, four-dimensional homology. It is clear, hopefully, that I can form a 4x4 period matrix. However, I mean, this is a 4x4 matrix, but I can put it into a 2x2 block form, where I write these four 2x2 blocks as A, B, A twiddle, and B twiddle, where the A is just the two first-kind differentials, so holomorphic differentials, integrated over the two A cycles. So it's matrix of A periods. The matrix of B periods in the same way are the two first-kind differentials integrated over the two B cycles. And A tilde and B tilde are just the quasi-periods, so the second-kind differentials, each integrated over the A or the B cycles. So this is our period matrix. So now we have to try to split it. And we can actually do this in a very similar way as before. We will need some type of Legendre relation. We will need some type of quadratic relation between the periods and quasi-periods. And indeed, this exists. It takes the following form, as you see below here. And this is now, however, a relation between 2x2 matrices. Also note the reason that this works now, or to make this work, I needed this technical modification of one of the master integrals, but okay, we can make this work. And then can split the matrix in a completely analogous way to before into a diagonalizable semi-simple part, which only contains the A periods and quasi-periods, and into a unipotent part, so matrix that satisfies a nilpotent differential equation, where some combination of the A and B periods appears, namely the ratio in some matrix sense, which is again the generalization of the modular parameter in the elliptic curve, here referred to as normalized period matrix, and as before is a very natural object on the hyperelliptic curve in the sense that it nicely parameterizes its geometry. Okay, so far the story is completely analogous to before, so it's clear what we should do. We should rotate with the inverse of the semi-simple part and see what happens. And indeed, this has a very nice action, and we can show that with some additional rotations. To be fair, this time this was not so simple. There are some technical complications, but really the key step still was the inverse semi-simple period matrix. But okay, after some additional rotations, we can indeed bring this into an epsilon factorized form. And we have good reason to believe that this is indeed the canonical basis that we are looking for. As I said, this is not perfectly well defined, but we can argue that this should be what we are looking for. And not only this, also this nice modular behavior that we saw in the elliptic case seems to generalize. There is some evidence that the entries of this matrix have some higher genus analog of this modular behavior. They're not modular forms in the ordinary sense, but so-called Siegel modular forms, which are the natural higher genus generalization of elliptic modular forms. However, I should say that there are also some important differences to what we saw in the elliptic case and what has also been observed in Calabi-Yau cases, namely that at the moment it seems like the quasi-periods don't seem to drop out, which miraculously happened in the elliptic case. At the moment, it's not clear why this doesn't happen. And also we seem to somehow need a new function in the sense that it is not expressible in terms of periods or quasi-periods, but is rather some integral with these objects. And at the moment, its interpretation is very unclear to me. This certainly didn't happen in the elliptic case, but I'm aware that, or we are aware that this does happen also in other cases. For example, the group that studied the K3 surface told us that this also happened for them. So this is not completely new, but the interpretation of this new function is certainly something one has to understand. So this is a work in progress, Doctor. So this is the current state. So I can certainly tell you that this method does indeed work. It generalizes to hyperelliptic curves, but the details still have to be worked out. So this already brings me to my conclusions. Here, I'm trying to sort of paint the picture that I wanted to convey in this talk. Namely, well, the first important point is that solving Feynman integrals in dimensional regularization, at least in our modern understanding, is equivalent to finding a canonical basis for the differential equation that these Feynman integrals satisfy. And finding this canonical basis is a very non-trivial task. And the modern the modern way we think about this is really through geometry by associating Feynman integrals with some complex geometry like an elliptic curve or something more complicated. And this will help us finding the canonical basis. And indeed, I mean, we saw in the elliptic case, for example, and the same thing also, of course, happens in the hyperelliptic case, that the canonical differential equation matrix in the end contains the elliptic periods in it. So it's very hard to imagine how we would find this canonical basis without understanding this connection to the geometry. So it seems like this is really a crucial input and crucial insight. However, still, if we understand the connection to geometry, it is still not an easy task to find the canonical basis in a concrete example. And to do this or to understand this better, I have reviewed that some people had on the leading singularity, which is actually an old notion known for Feynman integrals for quite some time, but it is again and again appreciated how it can simplify finding a canonical basis, and it seems to be, at least to me, it seems to be the correct language to think about this. And here I try to convey that sort of the period matrix seems like a natural analog of the leading singularity for more complicated geometries. However, it seems to be the case that actually it's not the full period matrix, but only its semi-simple part that takes this role. And of course, this picture is not complete. So this is not only my conclusion, but also my outlook. So I have said multiple times that this canonical basis is certainly very important, but not precisely defined. So this is certainly something that I would like to understand in the near future, what really characterizes this canonical basis. I mean, it's expected to always exist and be unique in some sense. And so if we have a precise definition, we could maybe even try and prove this. Also, I mean, I told you that there are a lot of geometries that appear for Feynman integrals. And so, I mean, elliptic curves has been actually studied quite a lot by now. Calabi-Yau varieties also have received a considerable amount of attention, but there's still a lot to be understood. But especially higher genus Riemann surfaces have not been studied a lot. So we have been studying hyperelliptic curves here, but it would also, of course, be interesting to see if this somehow generalizes to more complicated Riemann surfaces of higher genus. And of course, I mean, a bit the elephant in the room is this correspondence between leading singularity and semi-simple period matrix. The splitting of the period matrix is extremely ad hoc, in my opinion, and it is not at all clear, at least not to me, why this should be true, why this should be something useful. And so apart from heuristic explanations, to me, this correspondence is still very mysterious and should certainly be understood better in the future. So with this, let me end here and thank you for your attention.
Thank you, Sven, for your interesting talk. So let's move on to questions. Well, does anybody have any questions?
Hi, can you hear me?
Hi. Yes.
Yes, go ahead, please.
Hi, Sven. Nice to
Hi.
see you again. Thank you for your nice talk.
Thanks.
And thank you for accepting the invitation. And my question is, it is the same method if we have massless particles and massive particles?
Yeah.
Or it is any difference?
Yeah, that's a good question. So as a rule of thumb, the geometry or how complicated the geometry will be that will be associated to the Feynman integral depends on the number of scales in the problem. So if I have no massless particles at all and low number of external points, I will pretty much always have Feynman integrals corresponding to the Riemann sphere, and then I don't need the splitting of the period matrix because the leading singularity is just algebraic. So this really only becomes necessary if I include sufficient many scales. This can happen through many external particles. So I just have a bunch of Mandelstam invariants. But typically how it happens is that people study electroweak processes, for example, where you have a bunch of masses. So I would say that really this becomes important when you have many masses in the game.
Okay, I see.
In principle, it works in the same way for massive or massless. Yes.
I see. So, and what is the difference between cohomology and homology? That part is not. What is cohomology?
Yes, let me
Oh,
go back to this slide here. Yeah, so the two definitions you can see here, you
yeah,
can think of cohomology as differential forms and homology as contours.
contours.
Um, and so they are dual in the sense that they satisfy such a, or they you can get a number out of a pair of them. And they're also dual in the sense that it's not an accident that they have the same dimension. But I'm not a mathematician, so my way of thinking about this is one of them is differential forms and the other is contours.
Okay, okay. Thank you, Sven.
Okay, so
Mm,
another question.
I have a question. Do you hear me?
Yes, we can hear you.
Okay. Uh, Hello. What an amazing talk. I have a question about why is it important to compute master integrals?
Yeah, so thanks. Yeah, I mean, that's a good question. So, I mean, I introduced this notion of, let's see, your integral family, which, of course, at the outset introduces a bunch of integrals that I might actually not be interested in. But I mean, we can go at it from two different points of view, I guess. I mean, if I just want to compute one Feynman integral, then even if I'm introducing some additional complexity here, this differential equation method only works if I consider all master integrals at once. And even then, this is still the most powerful way of computing the Feynman integral. I mean, this is certainly not ideal that I have to introduce some extra objects to compute one thing, but this is the way it is at the moment. I mean, for special cases, if I have conformal symmetry, if I have finite integrals, I can study them in exactly 4 dimensions. I might not need this, but in the generic case, I actually do. So even if I'm just interested in one integral, I actually need all of the master integrals. But if I do a real physics calculation, let's say, so if I want to compute some process in QCD or so, then typically I have thousands of integrals flying around, right? And it turns out that actually many of these integrals fit in the same integral family. And so really I'm trading, I don't know, order 1,000 integrals for order 10 integrals, which are then the master integrals. So in a real physics computation, these master integrals are really a condensed set of the integrals that I have to do to evaluate this process.
Thank you.
Okay, so another question.
Oh, by the way, Sven, what a mathematical package you use?
So for the computations
Yes.
for the project, I'm not really using any mathematical package. So if
Uh,
you're, I mean, so I would say for computing differential equations, there are some public packages that I mentioned here. Here, so these are some references if you want. These are sort of algorithmic ways of computing the differential equation, but they will only work for Feynman integrals which are connected to the Riemann sphere. So all you will find are multiple polylogarithms. As far as I'm aware, there is no package that will do this beyond multiple polylogarithms. Maybe I'm missing something, but it's certainly not understood well enough, I think, to have a public package.
okay, okay, I see. Okay, thank you.
Well, more question, guys. Okay, I think there's no more question. So thank you, Sven, again, and we hope to see you again in the seminar.
Yeah, thank you very much.
Thank you. Bye. Have a nice
Bye.
day. Thank you.
Bye. Thank you, Sven.
Bye.